Yeah. They're like 30 minutes ago. Awesome. No. Little friend there. I could go up to Red Cross your name. Yeah. So it's funny that first often unfortunately, just wanted to make sure. See what the types of exercise. Respect to.
You mean use on the forces?
Oh, yeah.
Yeah, yeah, basically any force that has a component in the X direction. That's what you're gonna add to this equation. So any force, so all the vertical forces, the weights, they don't have any horizontal component. So those don't make it to the equation. But for the horizontal forces, yeah, J is there, and then FM is there as well. You take, yeah, FM cosine of the two things.
I found out that you sign. I don't get this answer, but you just have to simplify it out. They have A minus.
Yeah, well, that's going. We trade there. You get a lot of the.
Oh, don't worry, how far was that? It's-
What
It was on sale,
Nice.
and then your friend asked for the fund. Again, around like, what that would be. Because then you poured it in the bottom, then I don't think we can, and then it's okay. Well, no, it's.
Feel sick at all, but I've had this cough for like a week and a half now.
Now it's somewhere else.
Wait, yeah, but where did you go?
Sorry.
You did.
Yeah. I got one more.
It's like,
I got this. How much for it? And. Really? And usually they're like $3 a pop. That's what I was doing. I had a family in. Huh? And I use this one. Wait, what? And I really like this one. I'm kind of offended. Wait, how do you know? I mean, people like this when you told me. Oh. I mean, I didn't, maybe you want to. No, like I bought some more of this. If you want more, and just maybe $10. I'm teasing.
Schedule.
I'm teasing. I just kicked them all, so you just you're.
Yeah. That's $3,000 gone.
I think it was because me and my friend Sam, I wanted to go on a game contract because my friend Tyler. Yeah, he just wants to play hockey game with Sam. It's just going to and he's in the hockey team. And like Sam recognized him and I was like,
Oh,
this is
okay.
everybody.
so Sam, the engineering guy, went to a hockey game with Kurt, and I was at that hockey game.
It's the engineering
And do play hockey.
It's like Sam and John and Julie's like off
Hmm.
because my friend Tyler's in hockey.
All right, it's 4 o'clock. Let's go and get started.
Yeah.
Good afternoon, everyone. How's everyone doing today?
Yeah, how are you?
Good. I'm doing good. Thanks for asking. All right, so today we're just kind of chugging right along. So we are going to finish up, hopefully finish up our lecture note on constraint optimization. The hoping today will be the last day, but we may have a little bit of spillover on Thursday, depending on how quickly we go. And so by the end of this set of lecture notes, this is going to be the cutoff for the midterm exam. So first midterm exam is coming up in a couple weeks. And so I'm hoping to just have it be all just classical, all classical. So that's homework 1, homework 2, and homework 3, which I'm working on for you guys, and I should have it posted by hopefully, I'm hoping by tomorrow, but Thursday probably a bit more realistic. Just because I have some other things to do. Okay. Okay. Are there any questions I can answer before we get started? Okay. All right, so let's go and get started. Actually, the first order of business is that we did not quite finish our example from last time. So actually, let me go back to our notes from last week. Okay, let me actually come all the way back up here. All right. Not quite. There we go. Okay, this is the example. All right, I was tripping over myself a bit. Okay, so the last time we were here, we were working on this example here, right? And so in this example, what we wanted to do is we wanted to find the dimensions of a cylinder, which are its radius and its length, that will maximize the volume given its surface area, right? And so we basically are running a constrained optimization. We want to maximize the volume of the cylinder. But the one constraint that we have is that the total surface area of the cylinder must equal 24 pi. Okay. And so we solved this using the Lagrange multiplier method. And so what we first did was we formed our Lagrange function. Okay. And so we took our original objective function, which was the volume, which is pi r squared L. And then to that, we added our constraint in standard form, right? And so our constraint was lambda being our Lagrange multiplier, multiplied by 22 pi RL plus 2 pi r squared minus 24 pi. Okay, so remember that the quantity in the parentheses at the end there, that is our constraint in standard. Okay. And so from here, we went through our usual method. So we took our derivatives, we plugged back in and we ended up with this solution right here. So we said that in order to maximize the volume with a surface area of 24 pi, one way that we can achieve this is with the radius of 2 and a length of 4. Okay. And one thing that we did, one new thing that we did in this example that we didn't do previously was we actually went back and we plugged in for the Lagrange multiplier. So the Lagrange multiplier in this case was -1. Okay. Okay. And so we had two more tasks that we wanted to do with this example before we really moved on. And so the first thing that we have to do is we have to confirm that this solution here is indeed a maxima. Remember we talked about last week intuitively, we expect it to be a maximum because it doesn't make sense for it to be a minimum at all. But we'll run through the math to kind of show that that's the case. Okay. And the second thing that we're going to do is we're going to discuss, what does it mean to actually get a negative Lagrange multiplier? Like how do we interpret that? How is that information actually used? Okay, because that number actually does have some significance. And then it's, when we move on to inequality constraints today, the value of the Lagrange multipliers are going to have even more significance. So, we'll talk a bit about that before moving. Okay. Okay. So let's pick it up from there. Let me go back to week 5 here. So start with the clean slate. Okay. Okay. So let's start. The first thing we're going to do, we're going to confirm that our optimal solution was radius is equal to 4 or 2, excuse me, and length equal to 4 is a maximum. Okay. So actually, let me write down the Lagrange function one more time. So we have it all in one place. Okay, so our Lagrange function, which are the functions R, L, and lambda, is equal to I R squared times L plus lambda 2 pi squared plus 2 L minus 24. Okay. So we have a two-dimensional, 2D optimization here, two design variables, okay? Normally at this point, when we have to confirm whether this is a max or min, we would compute the Hessian matrix, right? We're still gonna do that here, it's just we need to do it in a slightly modified way because, we've kind of changed our objective function. Since since we changed our objective function to include the constraints, we have to do kind of a slightly modified approach to computing the Hessian. So just like before, we're still going to be computing second order derivatives. And so we're going to take our Lagrange function here, take the second order partial derivatives. We're going to take two derivatives with respect to R. That's going to be one term. Two derivatives with respect to L. That's going to be another term. And then of course our cross derivative as well. Okay. So we take the derivative R, then take the derivative with respect to L. Okay. But we also have to account for the constraints as well. So let me show you the form of the matrix that we're going to do. So if you remember from last time, the 3x3 matrix that we're going to compute here is L11, Z, L12, L21, 2 minus Z. We're gonna have 0 in the bottom right here, and then we're gonna have some terms that have to do with these meters. All right, so all these L terms here, so all the L's with the two subscripts here, those are second order derivatives of our Lagrange function. Okay, so for instance, L11 here will be partial squared L, partial R squared. L22, partial L squared, or partial squared L, partial L squared. Okay. Can't believe I had the opportunity to fix my notation for this and I botched it again. And so, that derivative looks weird because, I used uppercase L for the length of the cylinder. Uppercase L also is the Lagrange function, but, hopefully with context, you guys will. Okay. All right, and then L12 here, that is our cross derivative. So that is partial squared L, partial R, partial L. Okay. So those are very much very Hessian-like derivatives, right? So that's exactly kind of what we did with the Hessian. The only difference now is that we're adding the Z variable. Okay, and then the G variables here, the G variables are the derivatives of each of our constraints with respect to our variables. G11 here, partial G, R. G12, partial G, partial L. Remember, G is our constraint here. Okay, so what first thing we're gonna do, let's compute all of these derivatives just because there's just a lot to compute. So we'll compute each one and we'll put it in its place in the matrix after that. Okay, so let's start with L11. Partial squared L squared. Okay. So we're going to take the second order derivative of the Lagrange function with respect to the radius. Okay. So we're going to do that twice. Okay, so to come back up to the Lagrange function here, when we take the second order derivative with respect to R, we know that the only terms that are going to survive here are quadratic terms, right? Because if a term is linear in R, so let's say like this term right here, Even though that term has an R, right, we take one derivative with respect to R, it's gonna turn into a constant. We take another derivative with respect to R, and that term's gonna cancel out, okay? So we only have two terms here that actually are, going to survive. Which is this term right here, and this term right here. So we take the derivative of that first term with respect to R twice, we're gonna end up with two pi times L. Plus. We take the derivative of that second term with respect to R twice, we end up with a 4 pi times lambda. So you can see that our second order derivative here, it still depends on L and it still depends on lambda, okay? Remember that when you compute the Hessian matrix, you're evaluating the Hessian matrix at your optimal point, okay? And so we don't have to leave it in this form here. We can actually go ahead and plug in our solution. Okay? And so remember, our optimal solution here is L is equal to 4. R is equal to 2. R doesn't actually show up in this equation, so we're not going to plug in R. And then we have lambda is equal to minus 3. Okay. Okay, so let's go ahead and plug that in. We're going to get a pretty simple solution here. Okay. We're going to plug in for this L. We know that L is equal to 4. We're going to plug in for this lambda. We know lambda is equal to 1. Okay. And so we have 2 times pi times 4, which is 8 pi. And then to that, we're going to subtract 4 pi. Okay, so 8 pi minus 4 pi is going to give us 4 pi. Okay. So that is our top left term there, evaluated at our optimum. Okay, any questions on how we got that there? Cool. Okay, so let's work on the next derivative. All right, so our next derivative is L22, so that's the second order derivative of our Lagrange function with respect to our second design variable L. Okay. Partial squared L squared. So let's once again kind of go back up to our Lagrange function, and then we'll take the derivative with respect to L twice of each of the terms. Okay, and so if we take the derivative of this with respect to L, first thing we're going to look here is to see if we have any quadratic terms with respect to L, right? Because remember, we're taking two derivatives with respect to L, so there has to be at least an L squared term for something to be non-zero, right? And so we have a few terms here with L. So we have this pi r squared L. We have this 2 pi r L here, okay? But both of those terms are linear in L, right? So they only have L raised to the first power. And so when we take we take two derivatives with respect to L, those terms are just going to go away. Okay? Similarly, if you look at the other two terms there, so we have a lambda times 2 pi r squared. That term doesn't include any L at all. So after we take the first derivative with respect to L, that term is just going to go away. Okay? And then our final term there, we have a minus 24 pi times lambda. That term also does not contain any L, so that also is just going to go away. Okay? So our second order derivative with respect to L is actually quite easy here. Since everything cancels out, we just end up with a 0. Okay, so let's do the cross derivative. We have L12 equal 2 partial squared L partial R, partial L. Okay, so remember for the cross derivative, we're going to take one derivative of our Lagrange function with respect to R, then we're going to take that result and then take the derivative of that with respect to L. Okay. So I'll write this one out just to be a bit more clear. Okay, so first let's take the derivative of this function with respect to L. I think that's a little bit. Because remember with the cross derivative, it doesn't really matter which order that you take it in. You can take the derivative of L, then you take the derivative with respect to R, or you can go R first, then L. And you're going to end up with the same result no matter what order. Okay, so first we're going to take the derivative with respect to L of I R squared L plus lambda times 2 I R squared plus 2 pi L minus 24. Yes, question.
So another question on this one.
Oh, thank you. I totally missed that. Thank you for doing that. Okay. Question. Don't you have to distribute the lambda before you take the derivative so it wouldn't equal 0? Well, the lambda just comes along just as a constant, and so you can include it, or you can distribute it through, or you don't have to distribute it through. We're not actually taking any derivatives with respect to lambda, so in this case, it just ends up just being a constant. Good question. Yep. Okay, so let's take the derivative of this with respect to L. And so if we do that for this first term here, we end up with an pi R squared plus. So the lambda is just going to come along as a constant, and so I'm just going to leave it there. Okay. Then we have the derivative with respect to L of 2 pi R squared, and so that term does not contain any L at all, and so this term is just going to cancel out. Okay, so we're not going to have that in our cross derivative. Next thing we have there is a 2 pi RL, and so we take the derivative with respect to L, then the L is just going to cancel out. So that's going to be 2 pi R. And then we take the derivative of 24 pi at the end there with respect to L. 24 pi is just a constant, and so it's just going to cancel out as well. Okay, so we end up with this quantity right here. So that's the derivative of the objective function with respect to L. And then to complete the cross derivative, we then need to take the derivative of this with respect to R. First, we take the derivative with respect to L, then we take the derivative with respect to R. Okay, so if we do that, we just have two terms here to differentiate. So we have the derivative of pi R squared, and so that's going to be 2 pi times R. And then we have the derivative of 2 pi R lambda, right? We take the derivative with respect to R, we end up with 2 pi. All right, once again, we're going to plug in for R and lambda. So we're going to have R is equal to 2. And we're plugging lambda is equal to minus 1. Because that was our optimal result. And so we plug both of those things in, we get 2 pi. So those are the cross derivatives, and so that's a big part of our augmented Hessian. Any questions on how we got this here so far? Okay, But before we plug in, we also need to take the derivatives of our constraints as well. So we have a G11. Okay. So G1 here is partial G, partial R. Okay. So we're going to take the derivative of just our constraint. Okay, so remember our constraint for this problem. G of R times L is, it was 2 pi squared plus 2 pi R times L minus 24. Right, so that was our constraint. Okay, so the constraint being that the surface area of our cylinder has to equal 24 pi, and then we put the constraints in standard form. So we're going to take the derivative of this with respect to R, and so we do that, we get 4 pi R plus 2 pi L. Once again, we're going to plug in our result here. Our result was R is equal to 2, L is equal to 4. And so we just do the arithmetic, 4 pi times 2 plus 2 pi times 4. That's 8 pi plus 8 pi, which is 16 pi. All right, and then the last thing that we need to do is we need to take the derivative of the constraint with respect to L. So that is G12. We're going to take partial G, partial L. This is a lot more simple just because we only have one term here that has L, which is the middle term, 2 pi RL. So we take the derivative with respect to L, we end up with 2 pi R. Okay. Once again, we're going to plug in our optimal results. Our optimal result is R is equal to 2. And then we end up with a quantity of 4 pi for this. All right. So that was a lot of derivatives. And so the next step is to take these results here and plug it into our augmented Hessian matrix. All right, so let's go ahead and do that. And so if you forget kind of what the augmented Hessian looks like, I'm going to just scroll up here just very briefly. We're just going to plug everything that we just found into this matrix here. All right, so we plug that in. What we get is 4 pi, we get Z, we get 2 pi, 0 minus Z. And then top left, or excuse me, top right, we have 16 pi. That's mirrored on the bottom left as 16 pi. 4 pi. 4. And in the bottom right, we're going to have 0. Okay. So now that we have this matrix, we need to use it to determine if we have a maxima, right? Remember, that's kind of the whole reason we're kind of embarking down this journey. Okay. And the way we do that with constraint optimization is a little bit different. And so what we're going to do is we're going to take this matrix here and take its determinant. Now, if you recall, those z variables they're right now, they're still unknown, okay? And so by taking the determinant of this matrix, we're actually going to get a polynomial in Z. And then what we're going to do at that point is we're going to solve for the roots of that polynomial, okay? And depending on the values of Z that result, that's going to tell us whether we have a maxima or a minima at this point, okay? All right. So have you guys taken a determinant of a 3x3 matrix before? Probably a long time ago, but it's not the most convenient thing. So it involves kind of a lot of a lot of annoying kind of procedures. But okay, let's go ahead and do this, and because this is the only example that we have of this. So let's kind of go through every step. Okay. All right. So the way I take determinants of 3x3 matrices is that I basically do it kind of I do kind of matrices of I break it down into 2x2 matrices and take the determinants and then add and subtract. Okay. Okay, so this is what I typically do. So I usually go based off the first row, okay, and then I go term by term of the first row. So the first thing I'm going to do is I'm going to take the top left term, okay, which is 4 pi minus z. Okay, I'm going to cover up all the entries in the matrix that are the same row as that entry and the same column. And so what I'm left with at that point is a 2x2 matrix on the bottom. Okay? And so the first term of our determinant is going to be 4 pi minus z times the determinant of whatever's left. Okay. And so our first term, we're going to take 4 pi minus z times the determinant of the 2x2 matrix is z 4 pi, and 0. Just because we know how to take the determinants of 2x2 matrices, and so this form kind of makes it easier. Okay. By the way, this is just kind of my own preferred way of taking determinants of 3x3 matrices, and so if you have a way that you prefer, go ahead and use that too. Okay, so our next term is I'm going to circle the second entry in the first row, which is 2 pi. Once again, I'm going to cover up all the entries that are in the same row as 2 pi and the same column. Cross out this here, everything in that column. And then once again, we're going to take that entry 2 pi and multiply it by the determinant of the 2x2 matrix that is kind of remaining. And so, and one thing you have to remember here is that for the second term here, you have to do a minus sign, right? So the signs of each of these terms are going to go plus, minus, plus, minus. The first time we did was a plus. Second term, we're going to do a minus. We're going to do a minus 2 pi times the determinant of 2 pi, 4 pi, 16 pi, and 0. All right, and then the last term in our determinant here is going to be the last row in the last term in the first row, which is the 16 pi. Okay. Once again, I'm going to cross out all the entries in the same row. all the entries in the same column, okay? And then just do the same thing with the 2x2 matrix that's remaining. Good, plus 16 pi times the pyramid of that matrix there, so it's 2 pi minus z, 16 pi, and 4. Okay, and then all of this is going to be equal to 0. Okay, because we want to find the roots of this function right here. Okay. So we've broken down our 3x3 matrix. So now we have, these 3 determinants of 2x2 matrices. So the only thing here is just to kind of work at it a bit more. All right. So let's go ahead and continue. So let's evaluate each of those 2x2 determinants, and then that's going to give us just a single equation for z. All right. So first term that we have there is 4 pi minus z times the determinant of minus z, 4 pi, and 0. Okay. So remember to take the determinant of a 2x2, we're going to multiply the top left by the bottom right, minus the product of the two off diagonals, 4 pi and 4 pi. Okay. So we're actually saved pretty well here because we do have a 0 there. And so that 0 is going to cancel out that first multiplication. Okay. And so all we're left with here is 4 pi z times a minus, or I would say times 0, 16 pi squared. Okay. Okay. Then we have the second term, which is a 2 pi. We take that determinant of that 2x2, so we get 2 pi times 0, which is again going to give us 0 there. Okay. Minus 4 pi times 16 pi. 4 pi times 16 pi is 64 pi squared. And then finally, we have that last term right there. Okay, plus we have 16 pi times that 2x2 derivative, and so that 2x2 derivative there is going to be 2 pi times 4 pi. That's going to give us 8 pi squared. And then we subtract 16 pi times minus z. So the two minuses are going to cancel out. So we have a minus that comes out naturally because of the determinant, and we have a minus sign on that z term. So we have a plus 16 pi z. All this is equal to 0. Okay. So we're in a lot of luck here, and so if you look at each of the terms here before we start foiling and before we start distributing through, the maximum power of z here is just 1, right? So even though this looks like a scary equation, it's ultimately just a linear equation in z. And so solving for a single solution for z here is going to be quite straightforward. Okay. So that is quite fortunate for us. We don't have to solve any quadratic equation or any cubic equation or fourth order equation, you know, we're just gonna get one solution for. Okay, so the last thing we need to do here is just kind of distribute this through, okay? So let's go ahead and do that. And so first we have 4 pi times 0 minus z times 0, so that's obviously gonna be equal to 0. Then we have 4 pi times minus 16 pi squared, so that's minus 64 pi cubed. Then we have minus z times minus 16 pi squared, so that's gonna be plus 16 pi squared z. Next term is pretty straightforward. We have a minus 2 pi times a minus 64 pi squared. And so that's going to give us a positive 128 cubed. Okay. Then that last term there, that's just going to be a simple distribution as well. So we have 16 pi times 8 pi squared. So that's going to give us another 128 pi cubed. Okay. That was this term right here. And then our last term that we're going to plug in here is 16 pi times 16 pi z. And so that's going to be plus 16 times 16 is 256. 256 pi squared z. And all this is equal to 0. Right. So last thing we need to do in this problem is just to combine like terms and solve for z. And so let's combine all of the non-z terms first. And so we have a minus 64 pi cubed, a positive 128 pi cubed, another 128 pi cubed. Okay. So let's combine all those together into one. And so if we do that, we get 192 pi cubed. And then we're going to combine all the terms with z. So we have a 16 pi squared z up front here, a 256 pi squared z there. Okay. And so if we add those two together, we get 272 pi squared z. That's equal to 0. All right, so this was a long process. Right, so finally we can solve for our z variable here. And so we solve for z. So we're going to divide both sides by pi squared. That's going to take out the pi. We're going to divide both sides by 272, and then we're going to move z to the other side of the equation. Okay, we get z is equal to minus 12 over 17 times pi. And so since the z value is negative, this tells us that our optimal solution here is a maximum. And so if you look back in your notes, if the rules for Z here is that, thankfully the rules for Z are more straightforward than the Hessian matrix. And so if the Z you get is negative, then you get a maxima. If the Z you get is positive, then you have a minima. But if Z is 0, then you have neither a max nor a min. Okay. But since in this case, we have a negative Z, that means our solution here is a maximum of this objective function. Okay. Which is exactly as we kind of, suspected. Just because it wouldn't make sense for this to be a minimum of the objective function. All right, any questions on how we got this result here? Okay. Oh. Yeah, so when you have multi-dimensional optimization problems, you're going to be using the Hessian in some way to characterize the solution. Okay, whether you use kind of the classical Hessian, which is the just the second order derivatives, or for a constrained optimization, you would use this method right here. Okay, so you would compute an augmented Hessian. Okay. So before we move on to inequality constraints, I do want to take a second to talk about the Lagrange multiplier. Okay. So let's talk about the interpretation of the Lagrange multiplier in lambda. Okay. So let's take a step back and kind of remember everything that we've covered so far in constraint optimization, right? So far, we've only worked with equality constraints, and we've gone over 2 different methods to solve these problems. And so we have our direct substitution method, right? So with direct substitution, we basically took our constraint and we plugged it in directly into our objective function. And so what that actually resulted for us is that it actually ended up simplifying our problem, and we ended up, doing a lot less work, right? So direct substitution, if you're just interested in the solution, direct substitution is kind of the most direct and fast way to do it, right? The second method that we learned was this Lagrange multiplier method, where we kind of modified our objective function to include this Lagrange multiplier value, okay? And what we obtained from this is that, when we solve for our optimal solution, we actually get a value for this Lagrange multiplier as well, right? And that value actually has significance. And so even though the Lagrange multiplier method is more work, right? And so there's no kind of, there's no shying away from that. You do actually get some additional information about your problem that you don't get in direct substitution. So we actually get a value for these Lagrange multipliers, and they actually are, significant. Now, if you recall the way that we use these Lagrange multipliers, we use them in a way where we had one Lagrange multiplier for every constraint in our problem. Okay. For so far in this class, we've only done problems with a single constraint. But if you have problems with multiple constraints, in theory, you could have multiple Lagrange multipliers as well. And so because the Lagrange multiplier is tied very closely to its corresponding constraint, that kind of, tells us that, the value of the Lagrange multiplier will give us some information on that constraint. Okay. In particular, the value of the Lagrange multiplier will tell us what will happen, or it'll kind of give us some hints of what will happen if we were to modify that constraint. So think about, the last example that we did, right? So the last example, we constrained the surface area to be a value of 24 pi, right? Technically speaking, if you were to change the value of that constraint, and so let's say that you're constraining the surface area to be, twice that amount. So let's say that we're constraining the surface area to be 48 pi, right? Technically, because you're changing the constraint, you're kind of changing the entire optimization problem. And so you have to kind of go through and solve the whole thing again, right? Which is very cumbersome, right? So we spent kind of basically, cumulatively, probably an entire lecture on just that one example, right? So that's an hour, 15 minutes of work. And so, you don't want to solve a completely different problem just because you change the value of that constraint. And that can happen a lot in practice too, right? And so when you're doing kind of engineering design, you're going to have your set of constraints. The values of those constraints or the nature of those constraints, may change, as you go through the design process, as you're kind of working through different teams. You may think that you have more space or less space or more leeway, or more energy or less energy than you thought was required. Okay. And so getting some information about how your result is going to change with respect to the constraints is really valuable information. And it's one of the kind of the big benefits of using the Lagrange multiplier in particular. Okay. And so let me preface this by saying that, we're going to go over the different rules, right? So depending on if the Lagrange multipliers are positive or negative or zero, that's going to tell you different information. But the way that you interpret these rules depend on whether you're doing a maximization problem or a minimization problem. Okay. So the rules that I'm going to kind of show you is for a minimization problem. So that's kind of traditionally how, optimization theory is kind of formulated is in terms of minimization. Okay. And so keep that in mind. And so just know that if you have a maximization problem, just like we did in the previous example, the rules are kind of flipped. Okay. And you'll understand kind of what I mean by the rules are flipped in a second. Okay. But that's kind of important to note is that, these rules and most rules in general, most theories in optimization, they almost always assume minimization. But if you want to turn a minimization into a maximization, all you really have to do is just take the negative of the objective function. Okay. Okay. So let's go over the different guidelines. Okay. Okay. So if your Lagrange multiplier is positive, okay, so you have lambda greater than 0. And so in this situation, if you tighten the constraint, And what I mean by tightening the constraint, what I mean is making the constant value lower, okay, or smaller. And so if you think back for a previous example, to tighten the constraint, you would just make the surface area smaller, right? So maybe instead of 24 pi, you would lower it to like 16 pi or 10 pi or something. Okay. And so if lambda is greater than 0, tightening the constraint, what that will do is that it will make your objective function value small. Okay. Which, if you were doing a minimization problem, which is kind of what this assumes, is better, right? And so basically, if you were to tighten the constraints, you end up with a more optimal solution. All right. Guideline number 2. So you have lambda less than 0. Okay, so you have a negative lambda. And so in this case, if you tighten the constraint, this will result in your objective function actually growing in size. Which, if you're doing a minimization problem, is a bad thing, right? So your objective function growing bigger, that's not good, right? And so your result will become less common. Okay. So before I write the third rule, let's apply these rules to our previous example, right? So if you recall from our previous example, the Lagrange multiplier value that we got was -1. Okay. And so that puts us into this category right here. Okay. And so tightening the constraint, so making the constraint smaller will actually, grow your objective function. Okay. That's if you were doing a minimization problem, right? But if you recall, our previous example was a maximization problem. So even though we got a minus, a negative Lagrange multiplier here, we're actually going to be in this category. Okay? Because we were doing a maximization. All right, we're in that category, but we also have to kind of reverse things as well, okay? And so, so tightening the constraint in that case will actually make our objective function actually larger. So everything gets kind of flipped on its head when you do a maximization. So you're gonna see as we kind of go throughout the class, you know, even if we get maximization problems, it actually pays a lot to kind of reform the problem into a minimization. Just to kind of make the theory a little bit easier, because you know, once you kind of get into maximum minima and you read the theories, and you kind of get into a lot of kind of double negatives, and so it's really confusing. But and so you know, in you know, just intuitively as speaking, right? So if we think of our previous example, right? If we tighten the constraint, if we make the constraint smaller, right? So if we have less surface area to work with, that's going to lower our volume, right? Just you know, thinking intuitively, right? And so tightening the constraint actually in a maximization problem is actually going to be a bad thing. And so instead of a larger function value, you end up with a less optimal result. It's really confusing. It's you know, there's a lot of double negatives here, and so in reality, you know, it's easier just to kind of reform your optimization problem from the beginning as a minimization problem, and then you know, you don't have to kind of worry about all of these things, right? But I just want to kind of put this in context of the example that we kind of just did. Well, let me just go ahead and erase this just because it just, you know, you end up kind of tricking yourself into kind of you know, doing kind of the opposite of what makes sense, right? Okay. But the one point that I really want to make here, which is going to be relevant in our discussion of inequality constraints, is what happens if your Lagrange multiplier is actually 0. So if your Lagrange multiplier that you find from your analysis is actually 0, then what this tells you is that the constraint actually has no effect on the optimal solution at all. Which is a very interesting statement, which basically tells us that, you know, if the constraint has no effect, then it basically doesn't have to even exist, right? And so we would have arrived at this exact same solution, whether that constraint was there or not. So for this to happen with equality constraints actually is actually quite rare. You know, you'd have to kind of formulate the problem in a very kind of specific way. So, you know, this doesn't often happen with equality constraints, but this happens a lot when you have inequality constraints. Okay? And in fact, you know, this theory right here, this kind of you know, this argument is kind of central to kind of the main theory that we're going to go over, which is the Kuhn-Tucker conditions. Okay, and so with that, you know, we'll go ahead and transition to inequality constraints. And so, you know, there's not as much time as I would have liked, but you know, we'll probably finish this up on Thursday. Okay. Any questions on this section right here with interpreting the Lagrange multipliers? Okay. All right. So for the last 15 minutes today, let's talk about inequality constraints, and you know, we'll finish up the theory and we'll do some examples on Thursday. Okay. Inequality constraints, so. Let me start by saying that, from a mathematical point of view, using the pure classical methods. Inequality constraints are actually a bit more difficult to work with because, you'll have some situations where the inequality constraint is going to constrain the solution. And there will be plenty of times where the inequality constraints are not going to constrain the solutions. And sometimes it's really hard, or I would say most of the time, it's actually really hard to determine, whether the inequality constraints are going to make an impact or not. In general. So in general, inequality constraints are a bit harder to work with when you're using just pure classical methods, since, it's not always clear whether they're going to have an impact on the result. Okay. Because unlike equality constraints, and so if you kind of think back to how we interpreted equality constraints using direct substitution, right? Equality constraints defined a relationship that has to be satisfied in our result, right? And so that kind of, necessity, ended up actually, reducing our dimensionality of our problem, right? Quality constraints must be satisfied. And so what that basically means that, we had an equation that must be satisfied. It reduced the dimensionality of our problem by 1. Inequality constraints, they may be satisfied, they may not be. And so inequality constraints actually don't reduce the dimensionality at all, right? And so if you can have a 2D optimization with, 4 inequality constraints. And, even though you have 4 inequality constraints, you could still be solving a 2-dimensional optimization problem. So inequality constraints, instead of, making your life easier, it just ends up just giving you more headaches. And so one way that we can say that is that inequality constraints, by contrast, define a region in the design space where your valid solution has to lie. But it can exist anywhere inside that space. Let me give you a visual interpretation of that. Okay. And so if you were to, let's say that we have a 2-dimensional optimization. We have an optimization of 2 design variables, right? So we'll call them x1, x2. And so if we plot out the those two design variables, we make our horizontal and vertical axes x1, x2, just like before. Okay. All right. If we had an equality constraint, I have to be careful about how I say these, because saying an equality constraint versus inequality constraint, those are kind of different things, right? So let's say we have one equality constraint, okay? And so let's say that we have g of x1, x2 is equal to 0, okay? So that defines an equality relationship that has to be satisfied by our optimal solution, okay? Remember, what we can do is that we can take this constraint and we can plot it, right? So that's kind of what we did in homework 1. And so if we plot that constraint, let's say that we end up with a line that comes like this, okay? All right, so just as an example, let's say that this line is, x2 is equal to minus x1 plus 4, something like that, right? And so our equality constraint g of x1 comma x2, let's say that this was x1 plus x2 plus minus 4. Okay. So our constraint was, x1 plus x2 minus 4 has to equal 0. Okay. Right. And so if we move those variables around a little bit, we can plot it. We can plot the line x2 is equal to minus x1 plus 4. Okay. And so what this equality constraint tells us is that this line right here, this is telling us that our optimal solution has to sit somewhere on this line. Remember, for equality constraints, the constraint has to be satisfied, right? And so the only region that we can look is on this line, where that relationship of x1 plus x2 minus 4 is equal to 0. Okay. And so if you think about it, purely geometrically, we've constrained our space. And so instead of searching in the entire, x1, x2 design space, which is a 2-dimensional space, we're instead searching on this line, right? And so by doing so, we've effectively reduced our dimensionality from a 2-dimensional search space to just searching along this line. Okay. So we went from a 2D problem, to a 1D problem. Okay. Now, given that 1D problem is now kind of on a slanted line, but we are just searching along that line now. We're not searching in the entire 2D space. Okay. Okay, so if we contrast this this exact situation with let's say we're considering the same optimization, but we turn our equality constraint into an inequality constraint. So let's say that now our constraint g of x1, x2 is equal to x1 plus x2 minus 4. Okay. But now let's say that has to be less than or equal to 0. Okay. Right, so I'm using the exact same formula expression, except I'm changing the equal sign to a less than or equal to sign. Once again, we can rearrange the terms in this constraint here to be an equation. Okay. And so if we move terms to the other side, we have x2 must be less than or equal to minus x1 plus 4. Let's plot that line in our x1, x2 design space. Okay, so that line is gonna be the same, so that line is gonna be right here. Okay. But instead of saying that, our solution has to sit on this line, it is still possible for our optimal solution to sit on that line. But that inequality constraint there means that any solution where x2 is less than x2 minus x1 plus 4 is going to be a valid solution. Okay? So now instead of being on that line, we're instead defining this entire region right here. So this constraint, it is still technically constraining our problem, right? So there's that whole region above the line, which we can't be looking for anymore, okay? But if you look at the shaded region there, it's still a two-dimensional space, right? We're not searching all in line, we're still searching a two-dimensional space. It's a constrained space, or it's a limited space, but the amount of dimensions there is still the same, okay? So that's the challenge that we face with inequality constraints, is that, it doesn't actually make our problem more simple. We still kind of have to solve the full two-dimensional problem. It's just we have to do so by kind of respecting the constraints. And what you're going to see next time is that we actually don't have a lot of great methods for dealing with this. We do have a theory, or I should say kind of I would say a theorem, right? That kind of tests to make sure that everything is right, and that it utilizes the Lagrange multipliers. But what we're going to end up doing with a lot of these problems is a lot of guess and check. So we're going to solve for an optimal solution. We're going to pretend some of these constraints are active. We're going to find the result, check to make sure it satisfies everything. If that doesn't work, then we go with another. So it's a lot of guess and check, which is going to be frustrating. So I have two examples with this that we'll go over on Thursday. But those examples will take a lot of time just because they're a lot of guess and check. All right, any final questions on this before we head out for today? Okay, all right, so that's all we have time for today. And so when we come back on Thursday, we'll go over the conductor conditions. We'll go over how to solve these problems with inequality constraints. We'll go. All right, so thank you guys for coming today. I hope you guys have a good rest of your day. And I will see you all on Thursday. Thank you. Sure.
I felt good because I remembered all the determinants for X1.
Yeah, so what I would recommend for this problem, because there's a lot of content.
Everything did by the way I was. I did like how I plug into all the stuff. Okay.
Yeah, we're supposed to do that.
Not.
Yeah, no, I don't know if you've seen a lot of it.
Yeah, I didn't. That got first.
Guys, I'm like,
Yeah,
and then there's so and then you move.
It was like type it out,
Plus,
you'll see it.
yeah.
So I was getting like some.
I see.
I don't know.
I guess the only thing is that.
Yeah.
Free service?
Yeah.
Yes.
That's one of the.
I wanted to
Okay.
trade.
Okay, so I'm.
Yeah, it's exactly.
Okay.
Yeah, so make everything into kind of standard design. So
It was more like a tree.
Okay.
Not like an upper design.
Oh, yeah, I was gonna say watch on, you know. Definitely watch for it. I haven't seen that one. Also, Rise is one I watched recently that didn't even know about. It's sad, don't cry, but it's very good.